We want to be in view of the screens.
Okay, good morning, everybody. Thank you for coming for this new colloquium. Today we will have the talk by Dr. Jack Radcliffe from the University of Pretoria in South Africa. And he will talk about the next generation of milliarcsecond survey with SKA-VLBI. So Jack will be properly introduced by Anchor.
Okay, thanks, Rene, and welcome to our Severo Ochoa seminars. Today is a pleasure to welcome Jack. We have met several times across our lives. Last time was in Cape Town, 2 months ago, in fact, and we were having breakfast together. Okay, as Rene has mentioned, Jack Radcliffe, Dr. Jack Radcliffe is a senior lecturer at the University of Pretoria, and is also a UK SKA Regional Centre scientist at the University of Manchester. Jack conducted his undergraduate and master studies at Imperial College London. After that, he obtained his joint PhD degree at the University of Groningen and the University of Manchester. Then he was working in South Africa as a South African radio astronomy at the South African Radio Astronomy Observatory at Sarau with a postdoctoral fellow. And just now, as mentioned, he is senior lecturer at the University of Pretoria. He is leading just now the science support and community engagement at the UK SKA Regional Centre to help maximize the impact of the SKA Observatory and its precursors and pathfinders data. The main research interests of Jack are both technical and scientific, strongly focusing on high-resolution radio observations. Let me mention that he is a unique specialist in performing wide-field VLBI surveys of faint AGN. In fact, his previous work during his PhD has included pioneering radio interferometric calibration routines, radio transient and variability studies, and also on investigations of star-forming galaxies. He has a strong experience in software development, individually and also as a part of a team. And really, this experience has been obtained through the development of the multi-source self-calibration techniques, the European VLBI network primary beam correction scheme, and also on the co-founding of the emerging CASA pipeline. He has also an extensive teaching experience that has been obtained through 8 years of lecturing and workshop developments for the development in Africa with radio interferometry. This is the so-called DARA project. The foundation design and conduct of the inaugural radio astronomy lecture program for postgraduate students, also and the redesign of the undergraduate observational astronomy course at the University of Pretoria. Besides that, he has a strong link also to communication activities, and he has given compelling presentations at both national and international conferences, colloquia, and global outreach events. Just now, he's also the co-chair of the SKA-VLBI scientific working group, and he actively fosters and develops collaborations worldwide. Today, he will be talking about if you don't mind, Jack, yes, to read the title, about the next generation of milliarcsecond surveys with SKA-VLBI. Then, Jack, welcome again to the IAA, and the floor is yours.
Cool. Okay. Thanks so much, Anton. So hi to everyone online as well. So first thing I have to say is thank you so much for having me here. Grenada is a beautiful city. You're doing amazing science from what I've seen over the week. And I'd love to come and visit here again. It reminds me of South Africa and Pretoria weather-wise. I love the hot weather now. I've betrayed my British roots in this. So today I want to talk about very long baseline interferometry, which is VLBI. And I understand that many of you here don't do radio astronomy, don't do the very niche area, which is VLBI. And I want you to not worry, because I'm going to bring you into the warm embrace of very long baseline interferometry, and I'm going to hold your hand through all the amazing science you can do with it. And hopefully by the end, you might go, oh, well, this might be helpful for my science, so let me write a proposal. and come to the dark side of radio astronomy. So essentially, I'm going to start off. If you do VLBI, you can go sleep 15 minutes. I'll wake you up, have you, I'll come and shake you in 15 minutes time. Same for the people online, go make a coffee or something. I'm just going to talk a little bit about radio astronomy and VLBI and the differences differences that you have with standard observations. This doesn't work because I need to click on the screen. There we go. So this is where VLBI came from. It came from the quest for resolution. I always use this in my undergraduate courses. Everyone knows what the diffraction limited resolution of your telescope is. You can approximate it as lambda over d, where your resolution is theta. You've got lambda as the observing wavelength and your disk diameter of your observation. And the issue that you have in radio astronomy, of course, is that you've got very long wavelengths. So the Robledo DSM 70-meter telescope down in Madrid gives you about 1.5 arc minutes resolution at about 3 centimeters. Meanwhile, this teeny-weeny miniature refractor telescope on the side in about 600 nanometers will give you 6 arc seconds. So this is kind of where, you're not going to be able to distinguish which galaxy is coming from or even which part of the sky your emission is coming from if we don't increase the resolution. So we make bigger and bigger telescopes. There's the rest in peace Arecibo, which unfortunately fell apart. But even with a 305 meter aperture, I'm going to move over here, it gives you only 25 arc seconds resolution at 10 gigs. So this is, your human eye is as good as this. So, if we could see in radio waves, that'd be perfect. But we can get too big. This is, of course, the Green Bank telescope, the old version in 1988. And if I press the right button, that was the Green Bank telescope a day later as it falls on top of the observatory. And these things, these big, massive telescopes, A, are really, really expensive to make. And B, they're also structurally difficult to make too. Hence, we've got this now beautiful new Green Bank telescope, which has been replaced. So what we want to do is we do interferometry. So interferometry is to our rescue to get these extremely high resolutions. And now instead of having lambda over d, you have lambda over b, where b is the distance between antennas. And the linking of these telescopes basically allows us to what we call fill in the aperture. And I'll talk a little bit about that a little bit later, which means that we can improve our image at the end. So by having this distance between the two telescopes, you can arbitrarily put these telescopes wherever you want. Put them in space, put them on the dark side of the moon, put one in your bedroom if you really want to. But you can link them up and make them act as one. So this is an example showing the complete difference. This is, I always forget which one it is. Fornax A, that's the right word. At the bottom, this is the Sardinia radio telescope. It's 64 meters across. And this is the image of Fornax A you get with at 6.6 gigahertz, and it kind of looks blurry. It looks like when I don't wear my glasses, which is today. At the top, you've got meer-kat, the South African telescope. I work in South Africa. If I didn't put meer-kat in, I would probably not be allowed to go back in South Africa. But you can see the beautiful image that you get by having this high resolution. You can see all the extra structures. If that's that one, this doesn't. That's why. These beautiful structures you get by having the high resolution and high sensitivity that meer-kat gives you. And of course, you can see the thing that makes it, the little active galactic nuclei in the center. So this is why we have interferometers. So if I go the right way, and this is how it works. You can think of it. This is the way that I teach my undergrads, actually, if no one does interferometry here. You can think of it as a dish, which just has holes in it. It's a holy dish. And you can take parts of this dish apart, as you see on the right-hand side, these like mirror segments. And you can have the light rays coming in. They'll go the same path length from the source to your receiver. And then they'll add coherently and you'll be able to get your image. Now, with interferometry, as long as you know what that different path length is, you can just delay that signal going into your mirror segments and then align them constructively again. And that's all that interferometry is. It's just ensuring that your coherence of the incoming radiation remains the same. It remains in kind of constructive interference in some ways. Now, there is nothing that stops us from moving these thousands of kilometers away from each other, as long as we know how to delay that signal. So if you decided to follow what ERIS does, the ERIS school, you'll know all about this now. Now, typically we'll have connected interferometers. So these have a clock which goes to both antennas, and then all that you do is you delay the signal going into antenna 1 by this amount of time, this tau g. We call this the geometric delay. And then you would delay the signal so they add up in phase, and you know how constructive interference works. If it adds up in phase, then you get a big amplitude, you keep your signal, and then you put this to a correlator and you get your data at the other end. VLBI, and I'm sorry for everyone online who does connect interferometers, this is very, very simplified before you shout at me. For VLBI, it's a little bit more complicated. You've got telescopes separated by thousands of kilometers across the Earth, and you have to start aligning all of these. So the difference between what meer-kat does and what we do in very long baseline interferometry is that we get our telescopes on the other side of the world, we write the data to the disk, and we have an atomic clock which just stamps the data with the timestamp. And often you'll have people, it used to be people would come with luggage, with hundreds of hard disks in their luggage. I'd love to be stopped by customs showing this. It's like, what have you got there? It's like lots of noise. And you used to take it to a correlator where they realign the signals, and then you get your data set at the other end. And now you've basically got a data set which represents a telescope the size of the Earth. Now, one of the issues with VLBI is it's more complicated. So all these things on the right-hand side here are things we have to take into account. You have to take into account the fact that the moon makes the Earth's crust go up by 2 centimeters, because you have to align those signals. You have to take into account loading. You have to take into account thermal expansion of your telescopes. If your focus box gets slightly bigger because it got a bit hot, you have to take this all into account. So this is very complicated. Luckily, there's far cleverer people than I am that do this for me. So I don't need to worry about this. But because we can do all of this, we can, oh, that's just me showing the signal. This spike basically means that it's coherent. So we can do this now. I forgot about this. But because we've done all this, and this is based on 50 years of very hard work, we have these amazing arrays which can make images using a telescope which is the size of the Earth. And this is very long baseline interferometry. So you can see this is some of the interferometric arrays that are around. The one which is probably pertinent to you is the European VLBI network, but you've also seen the Event Horizon Telescope in all of the what's the right word? In all of the press articles that they seem to have, and the VLBA, this American array of 10 telescopes. And these go from a very broad frequency range, so you can go from 55 megahertz down with the International LOFAR telescope to 350 gigahertz. And as it stands, if you combine all these together, VLBI and VLBI arrays constitute the biggest collecting area on the planet of any telescope. So that's our humble brag for everything else. I won't tell you how sensitive we are in the end. So we've also got other arrays. So this is the East Asian VLBI network, the International LOFAR telescope, which goes at low frequencies, and the Australian Long Baseline array. So these are all the different arrays that we've got around the world. And the reason we've got all of these arrays, of course, is because, well, partially because some of these are in the south, so they can only see the southern half of the sky, but also they look at different frequencies, and the different baseline lengths allow us to do different science with each of these arrays. So that's a key thing to think about when we go forward. I'm just going to get some water while I... Okay. So we talked about VLBI. I need to talk about the other half of my my kind of hat, which is the SKA. And then I'm going to try and bring them together. And hopefully that means that you guys will want to use SKA-VLBI in the future. But if I've already lost you, then stay asleep if you wish to. So the other part of this is, and the other part of my job as SKA-VLBI chair, is to bring these two together, bring together the telescopes, which are all around the world, with the SKA. And I'm sure many people know about the SKA now, because I see you've had all of the chairs come before and give a colloquium. If you don't, then listen for 30 seconds. The SKA is going to be this amazing observatory. It goes by the mantra of one observatory, two telescopes on 3 sites. And we've got 2 of these telescopes. We've got the SKA-Mid. This is in the Karoo region in South Africa. And this is going to be at the same place that the meer-kat is. And it's going to constitute 133 SKA dishes, combined with the 64 meer-kat dishes. And it's going to go up to a baseline length of 150 kilometers altogether. So I don't know if anyone's managed to visit this place. I haven't. I've been there 5 years, but apparently it's very beautiful. Nice and dry, nice and high up. And these are our normal offset Gregorian satellite dishes, which are about 15 meters in diameter. On the right-hand side, we've got SKA-Low. So this is going to be 131,000 dipoles. They kind of look like Christmas trees. If I ever become a director in SKA, I'm going to ask for an SKA-Low telescope to hang up at Christmas. And these are combined into 512 stations. So there's lots of these Christmas trees, 256 Christmas trees in each station. And this is located in Murchison, so it's near where the Murchison wide field array is. And this has a 70-kilometer baseline. And the idea of this is it's kind of like LOFAR in the south. It's looking at 30 to 350 megahertz. And the third place is Manchester, UK. And I wasn't going to put a picture there because it's probably cloudy and not very sunny. So the SKA has a bunch of these science drivers. So what you can see here, this is all of the SKA science working groups. The best one is at the very bottom right, but you can see that it covers a whole load of science. This is a huge science remit for a single observatory. You know, you're going from looking at magnetism, you're looking at molecules being created in our own galaxy, all the way up to cosmology, the epoch of reionization. So SKA will be, what's the right word that I get paid? Truly transformational. It will be truly transformational. And, you know, the science drivers are huge. It's testing general relativity. You're looking at cosmic dawn, the very first stars, galaxy evolution, which is my jam, cosmology, but there's also going to be the exploration of the unknown. And you've seen this when Hubble went up, right? When Hubble went up, it decided to just look at a blank bit of sky, thinking there wasn't going to be anything there. And then the Hubble deep field popped up, and it was truly transformational in our understanding of the universe. So because the SKA is going to be an order of magnitude more sensitive, order of magnitude quicker to survey the sky, it's going to really, well, hopefully revolutionize and find stuff that we didn't expect as well. And I think that's one of the amazing things about astronomy is, you know, finding the things that were unknown before. It's why I do this every day. So you may ask, well, why do we still need VLBI? The SKA is going to do all this science for me. What will having telescopes on the other side of the world do? And this is a plot that we always use to sort of motivate why we need VLBI. If you don't do interferometry, it might feel a bit strange. But what you're seeing here is basically the bars represent the spatial scale, so the sort of size of the emission on the sky that each interferometer is sensitive to. The interferometers are a little bit different. It's not like an optical telescope where the most detail you can get is just based upon the size of your mirror and the illumination of that mirror. With interferometers, it's about, you can have kind of holes in that mirror, which means you don't see the largest scales. So if you have something that's fluffy, like it's called Fornax A image earlier, you might not see this if you don't have the short baselines or the short, like small mirrors, basically. And what you can see here is that this is the standard. This is a bit old. This is the very large array in the US. This is ASCAP and meer-kat, the SKA precursor telescopes. And this is SKA-Mid at the bottom. And at the bottom, you can see here, this is angular resolution at 1.5 gigahertz in arc seconds. And at the top, you've got a physical scale of about redshift of 1. So most of your distant galaxies are about 1.5 arc seconds or so. And you can see that with SKA-1-Mid, SKA-2 is not going to happen at the moment, but it might be in the future. You can see that there is basically anything below sort of an arc second or so, we can't look into that detail. We can't peer into the very heart of these galaxies. And this is, or the very heart of X-ray binaries or whatever your science case is. I'm very biased. But you can see at the top right, these are our VLBI instruments. And these are the only things that you are still going to be able to sort of peer into the incredible detail that you need to do certain science phenomena. And so SK1 or SKA will need global VLBI to be able to do this still. And by doing this, you end up getting and filling this graph, being able to go to the milliarc-second resolution scales you need to look at certain phenomena like black hole jet launching and things like this. If you have any questions, please do also stop me halfway through, because I know VLBI can be confusing. I still get confused, and I do this for 9 years. So what about the VLBI science that we can do? Well, with the SKA, we can do lots of things. One of the main areas is active black holes. I'm a little bit biased to this because this is what I do anyway. And of course, everyone here knows about the interrelation between star formation and black hole accretion and their co-evolution and the feedback mechanisms that you see. You see this on the right-hand side. This is showing negative AGM feedback. I don't remember this is why I put colors on, because I'm colorblind. The blue is the X-ray, the red is the radio, and the white is the optical. And you can see the radio jets emptying the cavities in this hot gas. And then it will heat up the interstellar medium and can stifle star formation. Stars don't like hot gas to form. And with VLBI is very good at finding these things. So if you're not sure, or if you've got lots of dust between you and the objects, radio is very good at looking through dust. It's not affected too much by extinction. And it means that you can kind of peer into the heart of these objects and look for the compact, bright things. This is an example by the Event Horizon Telescope by Michael Janssen. This is Centaurus A. And you can see the dust here. And if you didn't have these giant jets, you wouldn't be able to know what's there. So he can peer in and look and find these edge-brightened jets coming from the center of Centaurus A. And this is a milliarc-second, micro-arc-second resolution, not milliarc-second resolution. So this is incredible detail right close up to the black hole, which gives us understanding of what the jet physics is happening in these objects. Oops. Just a little bit as well showing this effect. We can use VLBI as well to sort of identify these objects in the sort of stereotypical deep fields. This is the only slides I'm going to have on my own science. I've got to do it somewhere. And when you look at the deep fields, you can identify your active galactic nuclei by morphology. I'm not going to give anyone a prize to work out which one's got the black hole here. Does anyone know? Well, it's going to be both of them because it's here. But not many of your sources are going to look and have this stereotypical jetty structure. Many of your sources, and this is a VLA image, will look like a blob, a boring point sourcey blob. And I can prove this. This is an image of the meer-kat field of the cosmos deep field. And every single one of these objects is a galaxy, but we don't know whether it's got star formation or AGN in the center. And we want to disentangle the two so you can start understanding how they're coupled together. You can see a few of the fluffy AGNs in here with their stereotypical jetty structure. But the key thing about this is that for 99% of those sources, you don't know what's causing the emission. So I'm just going to zoom in so you can see all the blobs. Blobology. Now we can do this with VLBI. So if you have a VLBI detection, this corresponds to high brightness temperature cores, and this equals an AGN. And when I talk about brightness temperatures, this is a horrendous terminology we use in radio. All it parameterizes is how much radio emission is coming from a small region. So it parameterizes both the size of the region and the brightness. So if it's small and compact, it's going to have a high brightness temperature. And that can only be caused by active galactic nuclei at high redshifts. You can do all the pushing starburst galaxies to a redshift of 1 and calculate this brightness temperature measurement, and it won't, there's a limit which it can't exceed. So we can use VLBI to look for these high brightness temperature cores. Here's our fluffy jets. Here's a VLBI image. Well, hey, there's a black hole there. Well, yeah, if you didn't get it from the other one, be worried. But you can do this with all the other objects as well. So you can start looking into these blobs, which you don't know what's causing the radio emission, and you can start seeing the evidence of AGN happening in these objects. And this is one of the key things, is that it's also independent of other multi-wavelength data. So if you can use X-rays to search for these things, search for AGN, you can use infrared bidding to find the torus of the AGN. But crucially, VLBI is also independent of all of this. It doesn't find everything there. That's the other key thing. And this is one of the modus operandi of AGN, of VLBI. So this is what people do, lots of wide field surveys of these objects, and it's all the papers at the top. That's mine in 2018. And people do these things all the time to try and find AGN using VLBI. There's lots of surveys. This is one now at low frequencies that we can do. This is 144 megahertz, I hope, at 0.3 arc seconds, which is remarkable. It hasn't been done before. Yes, okay. The other thing you can do with SKA and VLBI is to look at gravitational lenses. So the high resolution that you get afforded by having very long baseline interferometry allows you to constrain the lens model. And for anyone who doesn't know what gravitational lenses is, it basically means that you've got some mass distribution between you and a background source. And then that background source basically gets either multiple images or gets amplified by that intervening mass. Sort of like a, what do you call it? Oh, so this sort of gravitational lensing effect is very dependent on the cosmology and also the dark matter substructures of the intervening matter. Now, with having VLBI, this is a VLBI image on the right-hand side by Cristiano Spingola. This beautiful arc, because it's such high resolution, you're looking at milliarcsecond resolution, you can start to precisely work out what the dark matter substructure, or if there's any dark matter substructure which causes this deviation. So if you were measuring these things and you start to see a kink in the lens, then you know that there might be other sort of 10 to the 6 solar masses dark matter substructure in this object. If you have multiple of these, you can start constraining cosmological parameters. You can start looking at H0 in another independent way. So this is sort of a big area for VLBI to try and find these objects. There's like 2 or 3 of these things that we found up to now. We can also look at nearby galaxies. So going a bit closer to home, I don't do this stuff, so don't ask me questions. Going a bit closer to home, you can start looking at star formation with VLBI. This is the classic example. This is M82, one of the favorites. This is on the right-hand side. You can see Chandra in blue, HST in the green and the yellow. And you can see all of the gas, ionized gas, being blown out by the supernovae sat in the middle. And if we zoom in into the center, this is an image from the VLA showing this tenuous, these H2 regions, these supernovae going boom, blowing all the gas out. It's pretty amazing. And when you can go into higher and higher resolutions, so this is now with VLA and E-Merlin looking at arc seconds, that's that same VLA region, you can start seeing that way. You can start seeing the H2 regions and the individual supernovae, but these supernovae are unresolved. So you can only use VLBI to start resolving these things and tracking them as they go out in time. And the expansion rates of these objects, this is a new image that I made a few weeks ago, of these objects. By tracking them, you can infer what the mass loss rate of the original the star was. You can start inferring what the ISM is around these objects. Miguel is an expert in all of this, so it's going to tell me that I was all wrong in a minute, I can see. But this is some of the amazing stuff you can do in nearby galaxies. It's only the high resolution of VLBI that allows you to start resolving these things. And these aren't black holes. These aren't very distant black holes yet. These are, though. And everyone, if you haven't seen this, I don't know where you've been. I don't know what rock you've been under. But the other thing we can do with VLBI is, of course, image the shadows of black hole at extremely high frequencies. This is on the left-hand side is M87. The brush strokes show the polarization of this object. On the right-hand side is Sagittarius A star, as seen by the Event Horizon Telescope. And this is, these are remarkable images. It was amazing for the visibility of very long baseline interferometry, but it also allowed us to sort of understand tests of general relativity and lots of the black hole physics, lots of the AGN accretion, the jet launching and AGN accretion onto these objects, just by directly imaging them and measuring what the shadow looks like. So that's, it's amazing results. Yeah. Just to emphasize, this is like, if I remember right, it's if you get a donut and you put it on the moon, we're resolving that donut from here. So it's pretty amazing the sort of expertise and the engineering that needed to go into making this work. So I also wanted to talk a little bit more about the other science you can do. Hopefully these videos will work. Oh no. Okay, it actually works. Normally it doesn't. So the other things you can do are the science highlights that you can do with VLBI. One of the big things that you may have heard about is these things called fast radio bursts. Very bright flashes in the radio, which we didn't know what they were. People in the past probably actually just flagged them as bad data, your mobile phone going off and causing it. But we now think these might come from magnetars. And one of the issues with fast radio bursts was knowing where they came from. We just saw them in our data. And if you have a single dish, you've kind of got 15,000 galaxies it could come from. We knew they were far away. You can look at the dispersion curve, so frequency versus time it arrives. But with VLBI, you can actually start localizing it not just to a galaxy, but to a region in the galaxy. So is it coming from a star-forming region where you might expect there to be lots of magnetars, or pulsars, or exobinaries, etc. And this is an example. This is by Benito, who's here at the school eating lunch. And you localize this to basically the star-forming region at the edge of this spiral galaxy, just using VLBI. If you had a VLA image, it would constitute that whole spiral place and you wouldn't know where to go. The other thing you can do is look at ejecta from tidal disruption events. This is Miguel and his previous students' results, showing the ejecta coming from this tidal disruption event, which has never been seen before. So this is the first time you can do this, and it's only VLBI that allows you to track this over time at high resolution, understand how the jet was being launched. Is it going relativistic? Is it slightly closer to home? You can start doing nice little movies. Here's a microquasar, an X-ray binary. This is SS433. And on the right-hand side, you've got a VLBI image by the VLBA showing individual blobs of plasma getting accelerated and ejected from this object. There's the same by James Miller-Jones at the bottom. And this is the black hole position. And you start seeing these blobs appearing from the objects, coming off the black hole and being like pushed into space. And that's amazing information that we can use to constrain jet launching models and the environments of the X-ray binaries. The other science highlights you can do is we can start mapping the Milky Way. So you can start looking at things like mazes, and because you don't care about extinction, you can look through all of that stuff and start understanding and working out via parallax where the object is in space. So we can start doing this map. So you can see these dots are VLBI observations of normally mazes. And you can see they all align across the expected structure of the Milky Way, and you can start mapping this. You can also look at protostar feeding. This is by Ross Burns. I have to squint to work out whether that follows the spiral waves feeding this protostar, but you can also track your spacecraft and work out what is happening in the atmosphere as you're tracking your spacecraft with VLBI. And it's only the high resolution that allows you to do this. Some other weird things close to the home, we have, you can look at the size of your objects changing, which constitutes to a scattering media between you and the object. So if you look at background AGN passing through, say, a nearby galaxy, you can start seeing the source getting bigger because of scattering, and that gives you an indication of the interstellar medium, the ionized interstellar medium in these objects. This was by John Morgan back in 2013. But again, you can also look at astrometry. So you've got milliarc-second resolution, you can do astrometry, you can do multiple epochs at high resolution, and you can start looking at radio stars and the way that they're moving within clusters and constraining the kinematics. Lots of other potential science cases, YSOs, pulsars, SETI. You want to search for extraterrestrial life, go for it. The one other key thing, which is crucial to VLBI, is geodesy. So whenever you have a coordinate of your favorite object, that coordinate is basically anchored by VLBI observations, or at least it was until Gaia came along. What you're seeing here, this is the International Celestial Reference Frame. On the color scale, this is the semi-major axis error of the position. So you can see the majority of these are pretty much near zero. They're known to micro-arc-second precision. And the constitution of this allows us to define the reference frame that we use for our coordinate system. And it's VLBI that allows us to do this. And the reason for this is that we can turn our, remember those delay measurements where I showed you all those things that we have to correct for, we can turn VLBI upside down. And you can use the distant quasars to constrain what's happening on the Earth too. And this is geodesy. So what you can see here, this is coming from the same solution. Through VLBI observations, you can start tracking, say, for example, how the tectonic plates move to millimeter precision. So you can see here, anyone guess why the north of Europe is going up a lot? That's still rebound from the previous ice age. You can see the Australian plate ploughing into Southeast Asia, causing all the volcanoes. And you can only do this at this precision using VLBI. And because the ITRF underpins everything, so the terrestrial reference frame, it underpins how the Earth's moving, how the Earth orientation parameters are. Geodesy has an actual fundamental goal in a lot of development. So there is now a call showing that pretty much geodesy contributes indirectly to pretty much every UN Sustainable Development Goal. This is why the UN has a Geodetic Center of Excellence in Bonn, and VLBI is one of the ways that we measure this, basically. So there's a huge societal impact of this. The shorthand is if you used Uber around the city, you can only use Uber because VLBI has helped understand how the Earth's moving, and you can see where the satellite is. If you want to do smart agriculture, so if you want to maximize and move your tractor perfectly across your field, you have to know the GPS and you have to know where the satellite is. And you only know where the satellite is by knowing how the Earth's moving below your feet. So there's lots and lots of impacts of this going forward, and it's a big area that people are trying to focus on recently. So now we've come to talking about society and coming back to science with the SKA-VLBI working group. If this science, you think, okay, I think my science case could do with some nice high resolution stuff, please do join the SKA-VLBI working group. If you don't do VLBI, we don't care. If you've got really nice novel science cases, we can help you do those science cases. This is our poster. You can see it on the SKA website. On the right-hand side, I always put this up because I use it to sort of showcase how much we're involved with all the other science working groups and the other science. So what you can see, and you probably can't from the back, basically if it's green, there's people in other groups that are also in the VLBI working group. And we pretty much span all of the other working groups by a lot, apart from solar. Don't want to look at the sun anyway. No offense to anyone online who likes the sun. There you go. So in the final part of my talk, I'm just going to go into more details of how SKA will work on the how VLBI will work on the SKA, and I'm also going to talk about some of the new developments around the world which will contribute to VLBI with the SKA. Just as a shorthand of this, as a prequel, this is how SKA-VLBI will work. SKA will work like this. There's going to be a lot of data going to a central signal processor, to a science data processor, to an SKA regional center, and then you'll talk to me to get your data. The key thing about this is that nobody will need to reduce radio data anymore. So ERIS should hopefully be defunct when the SKA comes online. But we'll see. But you can see the huge amounts of data that's coming in. This is petabytes per second from SKA-Low. And by the time you get the data products at the other end, it's going to be 700 petabytes a year. So yeah, good luck using your laptops. You've got SKA-Mid, this will be processing in Cape Town and then Perth as well, the SKA regional centers. VLBI is a little bit different. VLBI is the only one that won't follow this mantra specifically. With VLBI, what's going to happen, I'm going to be like that, the picture. With VLBI, what's going to happen is that we are basically going to take our SKA-Mid antenna. This is the primary beam, that's basically the bit we're sensitive to. And we're going to combine these all together with other telescopes and make it what we call a subarray. It's just an interferometer, a subset of those telescopes. And within that subarray, we tie them up, we phase them all up together, which just means it's a fancy word for making it act as a single telescope with the distance between the two. And then we pump that out of SKA and it goes to an external VLBI correlator. So that means ERIS doesn't matter. It'll just be SKA-VLBI ERIS because you're going to need to reduce your data. Now, the key thing about this is a plot showing the comparison. So here we've got the Effelsberg 100-meter telescope. And if we compare this to what SKA-Mid is going to be, this is these lines here, it is orders of magnitude more sensitive. For the non-radio astronomers, SEFD basically means sensitivity of my array and not the acronym. Of my telescope and not the acronym. So Effelsberg 100-meter telescope is about 19 Janskys SEFD. When we look at SKA-Mid, you're looking at 2. So this is orders of magnitude more sensitive. Yeah, I'm not going to go into Janskys. And you can see this on the right-hand side, where you can see the sensitivity, where you have the full array combined together, and in micro Janskys, you're looking at 1 or 2. So this is amazing. It's sort of a kind of having a 300-meter antenna in South Africa going forward. We've got a nice milestone for SK. So we got meer-kat working in VLBI finally. Whee! So this is the meer-kat telescope, beautiful. On the right-hand side, basically, if there's a big spike in the middle, we've got nice coherent constructive interference, and this is an amazing step. And we're hoping in the next sort of year or two, meer-kat VLBI will start to be offered as an operational mode. I hope Fernando's not watching this. To supplement SKA-VLBI, we have this African VLBI network program. So I think in my introduction, when I was talking about DARA, on the right-hand side, you can see this is the original SKA-2 plan, where you have these SKA outstations going across the whole of Southern Africa to give the high resolution. And then we were going to basically convert existing satellite dishes to new arrays. And as part of this, we also wanted to build the human capital development as well. So the DARA program, which I've been involved in for a few years, would send astronomers from Europe and South Africa to teach people who have just finished their undergrad degree in astronomy, because they don't necessarily have an astronomy group, they don't necessarily have a course teaching them how to observe with the universe. And then the idea was that these people would then go and set up their own groups, build astronomy, but also lots of the skills that you learn as a PhD student are really applicable in other parts of industry, right? How many computing languages do you all know in this room? It's probably most of them in the world. I'm sure there's people using Fortran 77, which I learned when I first started. But it's really applicable. So we've got a few people here teaching at Eris who went through the DARA program. And the idea is that, you know, we want to build this network across Africa to fill in the gaps in our telescope and make even better images of the SKA-VLBI. So on the left-hand side, this is one of the success stories. This is the Ghana Katunze telescope on the images here. It's this one here in Ghana. I live here now. And this is a 32-meter telescope, originally for telecommunications, and it was converted into a radio telescope. It now observes at C-band, and we hope to see that it gets more bands going forward. Now, the idea is that it was going to fill in these gaps. This is a UV plot. For those who don't do radio astronomy, the blue is the bits before the AVN, and the red is the extra parts. And the more filled in this is, the better the images you get. The more detail you can see, the more structure you can see. Now, the AVN, that original idea didn't really work, but now we've suddenly got a new impetus to build more telescopes. So the Dutch Center for Astrophysics, the German Center for Astrophysics, DZA, now has an agreement to build a telescope in Botswana. So this is the agreement signing here. And in the Karoo, we've also got the SKA Max Planck Institute telescope in the Karoo. And this was the first images it was making of the whole sky in single dish mode. In Europe, we've got new initiatives to build arrays. One of these is RAZR. This would be a 12 SKA-Mid dishes across the UK. You've got co-observation with SKA because it can look at the same bit of sky. It's on the same longitude. And this would extend the baselines of email into 800 kilometers. It's still in a prototyping phase. We're hoping that the phase 1 will get approved in the next month or so. But this will be amazing for high resolution science, but also space tracking, space weather monitoring, rapid transient follow-ups when the EVM's not online, but also combining it together to be working with the SKA too, because it's going to be SKA dishes, hopefully with SKA receivers. In addition to this, we've got Leverage. This is the German initiative. I forget what Leverage acronym is because it's very long. Astronomers are very good at making acronyms, like out of middle of the words as well. I think. But the idea for this is that Germany is positioned such that it can both use the SK and the new upgraded very long baseline VLA, the very large arrays, so the NG VLA. And this will add long baselines from north to south between SK and east to west between the NG VLA as well. And what you can see in the middle, this is an NG VLA image of a I think it's M87. This is the source model showing the black hole shadow. With the NG VLA, you kind of get this smudge, but by adding the long baselines of the Leverage, you'll start actually being able to see the shadow of the black hole going forward. And the first of these telescopes is currently under. I think they're negotiating getting the money. In addition to this, we've got VLBI that's popping up everywhere. Everyone wants to do VLBI now, so please join in. We've got the Thai National Radio Telescope. This one's operational. It's 40 meters. This is fringes. The spike again means that we got coherence between Effelsberg and the Thai National Space Telescope. Looks kind of similar to IRAM. Wonder why. And this can go up to high frequencies and all the way down to L-band, I think. And people are building these arrays everywhere. This is the Southeast Asian network. I saw this at the EVN. There's going to be hopefully some in Indonesia, some in Vietnam, 3 in Thailand. I think, don't hold me onto this, people online. I think it was like the wish of the late king of Thailand because he's really into astronomy. And then the princess loves astronomy. She went to Jodrell Bank last year, and yeah, so they're really pushing building these arrays going forward. For SKA-Low, it's a little bit different. These are normal dishes. For SKA-Low, this is the Christmas tree I was talking about. You kind of direct these on the sky by phasing them up. And for SKA-Low, it's a little bit different. With VLBI, it's a little bit different because there's less of these stations. People don't want to make these dishes. It's a little bit more difficult. It's going to work the same way. We're going to beamform these objects. So you tie them up together and you make little fields of view, and then you correlate it externally. Again, this is an order of magnitude more sensitive than before. LOFAR is somewhere above this plot. So the current best is LOFAR in the Netherlands, which is above this plot. We're looking at SCFDs, which is kind of 10 Janskis, which is remarkable for low frequencies. But one of the problems we have with SKA-Low is actually complementary telescopes. So getting the long baselines is more difficult. So this is a rather old plot before I've showed all the other ones in Southeast Asia with the dishes. But even with this plot, you can see in green, you can see the SKA-Mid complementary objects, which you could possibly combine together. In red, you can see the SKA-Low ones, and there's very few comparatively. And I stole this and call that because it works well. So one of the goals, actually one of the new initiatives, is this Lambda project. This is the low frequency Australian megameter baseline demonstrator array. We'll change that one as well. And this is to add long baselines. I'm almost finished. So this is to add long baselines to SKA-Low. And the idea is that at every LBA site, we put an SKA-Low station and you get high resolution images. So you can start using this to do low frequency astronomy, looking at AGN, star formation, exoplanets, everything that LOFAR is doing in the south. There's currently funding, I think, to develop Lambda. So there's now project scientists. And they're also looking at combining the MWA with SK. So this is hopefully this gets off the ground, because this would be an absolute boom for SKA-Low VLBI science. And it's something we really need to work on. So the other thing I want you to be aware of is there's going to be a new book for SKA. So if you want to know more about SKA-VLBI, remember this talk a year from now, because that's probably when the book will come out. So if you really want me to come back, and I'm more than happy to come back to Granada. We've got this book coming out, and at the moment we've got about 45 chapters showing the SKA-VLBI science, or including SKA-VLBI science. And if you think that your science case could also be covered by this, please do contact me, get involved with the book, help people write it. Because the one thing we realize with VLBI is it's very niche. Like, all the people know each other. And so we want people from the outside to come and see what it can do for your science too. So summary, this is VLBI basically produces the highest angular resolution images. This is unobtainable with the SKO, hence why we exist. It's got loads of applications: galaxy evolution, cosmology, jet physics, star formation, astrometry, geodesy, transients. Oops, hopefully if I'm doing this. And the SK will provide basically a huge boost in sensitivity in the Southern Hemisphere, especially when we combine with all these new amazing initiatives going on around the world. There's lots of work to be done. We need to start having more emphasis on SKA-Low. We also need to work out operational models, how SK will actually work with all the other arrays. But if you are interested, please do email me or email my co-chair, which is Yun in Onsala, and I'll take any questions if you haven't fallen asleep yet.
So I take a little bit of credit on Teresa for inviting Jack, and coincidentally he was going to be here anyways for Eris, so it was an awesome situation. And I'm very happy we did invite him, because this was excellent and I learned a lot. I thought I knew all the initiatives going on, but I did not. Like, half of them were.
I didn't until a month ago, so
Anyways, so I get the honor to lead the questions. So if there are any questions in the audience here. Otherwise, I have a couple.
Scare people off.
Oh yeah, nervous. Sorry.
Yes. I was wondering, you were speaking about meer-kat and doing VLBI with meer-kat. How is it going to be complicated when meer-kat becomes part of SKA, because this is itself already complicated?
Good question. Yeah, what's the right way to put this without losing my job? No, the short end is that I think for the meer-kat VLBI stuff, this will be offered by SRAO, South African Radio Astronomy Observatory, until it becomes part of SKA. And then as soon as it becomes part of SKA, SKA will take over whether they give VLBI at certain times. So as far as we know, SKA should have a VLBI mode when they have what they call AA star, which I think is 2028, 29, somewhere around there. And by that point, when AA star comes on, meer-kat will be subsumed anyway. So it should hopefully be complementary, where meer-kat might offer VLBI, and then as soon as SKA is big enough to subsume it, SKA should offer it. So there shouldn't be a gap. But the politics behind it is also quite complicated, as far as I can see.
Thank you. Well, I'll take the opportunity to ask one too. This is more a little bit about the science working groups.
Sure.
We have invited a co-chair from every science working group, and there's 2 more to go now. You're the third last one. To talk about their science. Now, the VLBI working group is very different in that it's a technology rather than a science area.
Yeah.
So I was wondering, like, how do you keep track? It should really be the science working group with the most membership in this sense, because it seems like everyone who is in any other science working group should be in the VLBI as well, if they want higher resolution. But like, do you have more co-chairs than the other groups? It seems like you should.
It keeps me up at night, this. No, it's I like to think we've got spies in all the other groups, and but yeah, it's rather we just have to keep. Us as chairs, we keep track of what everyone else is doing, but there's only so much we can do. And yeah, we're hoping that at least with this focus with the science working books, we can start
because you didn't exist. The VLBI one didn't exist for the 2015 science working groups, right? So this will be all new.
This is all new, yeah. So, and also this is where we're kind of careful as well, because we can also get sort of being like a footnote in a lot of different chapters, because we're kind of like, you can do VLBI, which helps with this. So we really want it to be a science working group so we can highlight, but also have that visibility to make sure that this is a mode on the SKA, because it would be a huge advantage to the high resolution science. Yeah, this is the weird thing. We're kind of a technique, but we cover lots of science cases, and yeah,
it's interesting. Well, you gain another member if I may join, because I just found myself on an EVN proposal, so
okay.
I'd like to keep in touch more.
Welcome.
Any more questions? Yes.
So you mentioned that the original AVN project, as far as I understand, is no longer considered. What was the issue? Can you elaborate more on this?
People online will probably shout at me, but this is how far as I know, is that it's very expensive to refurbish dishes. So there was a lot with the Ghana refurbishment. It was more expensive than they thought it would be. So it was actually probably cheaper to just buy an SKA dish going forward. And that was something that you only learn by doing, unfortunately. So that, I think that's also why things never went forward, but very recently it's sort of been revived in a different sense. So we're hoping that with some of these other initiatives, so there's sort of initiatives which actually use very cheap small dishes, lots and lots of small little dishes, which are easier to maintain, cheaper to install. They're like 50,000 euros compared to 2 million for an SKA dish, where you can put them in and use that as an array instead, which would then bridge the gap between having an SKA dish in these countries and not. Yeah, no, I think that's the main reason it was a lot more expensive to refurbish than we thought. But I'm trying to get one in Kenya because I live in Nairobi now, so something to do.
Anyone else? Well, then I suggest we thank Jack again for this excellent. And a few of us will be heading for lunch afterwards. I think there could be one more. Let's see for one more if anyone is interested.
Okay, thanks a lot. Thanks everyone online. Appreciate it. Yeah.
Do you have anyone in your group